So we're going to finish up the notes we didn't do on Friday, and we're going to look at apparent size, which is just an application of the arc length formula. So the arc length formula being our S equals R theta, where S is the arc length, think the pizza crust, R is the radius, and theta is the measure of the angle in radians. So it gives you a quick example, and it just shows you how when you look up into the sky, the sun and the moon actually look very much the same size. But in reality, the sun is much more larger than the moon is. And so it has to do with the actual distance that the object is, as well as the angle at which you are looking up at it. So apparent size, by definition, is actually the measure of the angle at which you look up at something. So if you're thinking of yourself looking at an object and you're looking straight ahead, so if I draw a straight line, calling that the line of sight, and then you're looking at something up here, so you look your eyes up at something, this right here, this theta, is the measure at which you're looking up, the angle measure, and that is what we're going to call apparent size. So here's an example, and this comes straight from your textbook. It says Jupiter has an apparent size of 0.01 degrees when it is 8 times 10 to the 8th kilometers from Earth. Find the approximate diameter of Jupiter. So before I do that example, I just want to do one quick other thought process to help you understand this. Think about how when you're driving down a road and you're seeing a mountain very far in the distance. So when you're really, really far away from that mountain, it's going to look super small. So the angle at which you're looking up at it, of course, is going to be this theta. The closer you get to that object, so as you get closer to that mountain's going to look very tall. And so the angle at which you look up at that is going to change and become greater. Now, the further you are away from the object, the more it is that apparent size, the angle will change, but more importantly, the more the arc length actually represents or is close to the height of the object, also known as the diameter of the object. So if we look at something like this, over here, my mountain when I'm super close, let's say that this is the radius looking up to the mountain. And so that here would actually be a little bit further. So our circle would probably look something like this. So the arc length of that sector is not very close to the height of that object. But the further we go away, let's say that this is my radius here, when I bring that radius out this way to the bottom of the object, it's only going to go slightly further. So if I was to draw this entire huge circle, sorry for how awful this is going to come out. Here is the arc length of that circle, which is very similar to the height of the mountain. So you are going to be able to use the arc length and the arc length formula to approximate the height, or in this case, the diameter of the object. So think arc length, S, is going to equal the height or the diameter of the object. And as I've mentioned before, this is my radius, this is my radius. So the radius is going to be how far away you are from that object. So the distance away. Because we're assuming, again, the farther you are, the close comparison we have here to the radius and the actual distance. So let me just erase all of this here so I can go through this example. So looking at our picture, it's saying the angle is 0.01 degrees. We will have to change that to radians. The radius, the distance away, and I want to know the arc length, which as I mentioned above is going to be our height or diameter of the object. So using the formula, S equals theta R, or R theta. S is the unknown I'm searching for. Theta I'll fill in a minute. And then the radius is 8 times 10 to the 8th kilometers. And I said I'd fill in theta in a minute because theta is in degrees right now. and we will have to change that to radians. So remember, 1 pi radian is 180 degrees. This way the 180 degrees would cancel. So it's going to be 0.01 pi over 180. And this, of course, would absolutely be a calculator problem. And if you were to do that in the calculator, it would come out to be approximately 139,626 kilometers tall. And one that is a little bit easier to use, and I had put it in radians for you with very similar numbers, is the mountain idea that I had just given you an example. So suppose you're on a road trip and you spot the mountain up ahead. So here's your car, here's your distance away. That's going to be what we use as our radius. It says we're 20 miles away. Here's that mountain, which we are going to use the arc length to approximate the height. And then the angle at which we look up at something is our theta. And again, I'll repeat one more time. This doesn't say degrees, so we're understood to be in radians. So that's good because we can plug right into our formula. S equals theta r. So S, once again, is my unknown because we're looking for the height, which arc length is approximating. Theta is 0.01, and then the radius is 20 miles. So when we multiply that, we will get 0.2 miles. And that is actually our answer, except for one thing. It asks for the answer in feet. So this is where we do our dimensional analysis. We have our 0.2 miles. We'll put it over 1. And then to get rid of miles, it'll be in the denominator. And we have 5,280 feet in 1 mile. And when we multiply, we'll get 1,056 feet high. Once again, I'll do another example or two in the second day of notes, so hopefully by the end of those, this will help make some sense of this.